Hello, this Abjoin Babatunde Bukola again for this channel, Nuclear Process Designer. Today, although it has been a long time since I released video, so I'm back again. Today, I brought to you an exclusive content on process integration, heat management and integration on Aspen Plus. I have a flow sheet of a refinery here for refining a Mexican crude that we call Maya crude from Mexico. So for the Mexican crude, I think I characterize it with properties environment, but that's not the main point of interest in this video. We have the flow sheet for the refinery here. We have the atmospheric column and the vacuum column. And for the atmospheric column, we have reflux drum, condenser, and a furnace. For the vacuum column, we have a furnace. I will be going deep into each of the main column because it's a refinery crude unit for a refinery. So, and we have pumper and strippers in each of the columns. So it's a typical refinery process for refining Maya crude. And each of the pumper there is coolers to cool the circulating stream for the column, and in the strippers we have the products. For example, in the atmospheric column we are getting turbocene, which is aviation fuel. We are getting kerosene, diesel, and atmospheric gas or vapor. So, and for the vacuum column we have the atmospheric vacuum gas or VGO. Then we have the light end, which is this stream for the vacuum column, and both column they are same strip. You understand? They are this one is a reflux absorber. For this we have a top pump parent for our condenser, and it's also having a furnace. So then I specify the furnace temperature and for the column. The main point of interest is because of the crude is coming at a typical room temperature 13 degrees Celsius, and we need to increase the temperature of the crude to very high temperature because the furnace temperature is 395. So in order to integrate the heat of the product, because the product is coming at very high temperature, that's the main purpose of doing heat integration, is to configure the flow sheets or arrange the flow sheet in such a way that we are using minimum utility for the system, because we are expecting to get high temperature products from the distillation, vacuum, and atmospheric distillation, and we need to increase the temperature of the feed, which is the crude oil. So we are going to reintegrate the heat of the products back into the feed, and that's the work of this heat exchanger train that we call preheat train in the heat exchanger. You understand? So it is to increase the temperature of the crude to a very high temperature that we are getting 301 now. You understand? So I'm going to, in this video, I will be explaining how this is done and how to optimize this heat integration and design efficient heat exchanger network for refinery units with Aspen Plus. So, and for the heat exchanger network, it is there here. So you have series of heat exchangers that are intertwined, connected with the product stream, and they are exported. Then we have the utilities, the coolers and the heater For example, this is the furnace that has been duplicated in the heat exchanger network, and the coolers to make sure that we are getting the product specified temperature, because we must get the product, cool down the product as we are drawing the product out of the atmospheric and the vacuum distillation column. For example, this is the aviation fuel drawn out of the atmospheric distillation column, and this is the stripping strip for it, for the stripper. Then we have the kerosene. It is cooled down in the heat exchanger train, the diesel and the atmospheric gas oil, while for the vacuum column too, this is done for both the pump around stream and the product stream. Even for the pump around stream, you can see for the atmospheric column too, they are also sent to the heat exchanger column in order to reduce the cooling utility needed for the pump around circulation. For the vapor, we have the condenser. Condenser too is also integrated in the heat exchanger train. You understand? So and we have the reflux drum over here. You understand? So this is the flow sheet. So in this work, we are able to get 301 degrees Celsius for the outlet temperature from the heat exchanger train. So, and we want to optimize this network. We want to optimize this network with Aspen Plus, so that we can increase the crude outlet temperature from this heat exchanger train. So, in order to do that, there is although I've done that before, I have specified the temperature of the heat exchanger network and connect it in such a way, because what I'm doing currently is just a rating design, rating optimization of a process. I use a refinery process for it, and so there are some specifications for the heat exchanger. So I will be adjusting those specifications in order to increase the outlet temperature of the crude from the heat exchanger train. So in order to do that, we use something called the activation dashboard. For example, there are some software that is done by Aspen Tech, like Aspen Energy Analyzer, Aspen Capital Cost Estimator, and the Aspen Exchanger Design Rating. We can integrate those software with Aspen Plus, with our model in Aspen Plus, in order to do some energy calculation, energy analysis on our our model in Aspen Plus. So I'm going to be using the energy analyzer. So you use it through this, you connect this Aspen Plus with energy analyzer through this activation dashboard. Then you want to set up the model to calculate. So I'm going to open it through this method, although you can also do it by going to the energy analyzer tab here, analysis tab, sorry. Yeah, it is to do it, you understand? So, but let's take it one step. Then you define the process type. The process type is a crude unit. You can define the approach temperature for the energy analysis. That is, it will calculate the theoretical amount of heat that can be exchanged in the model connection, you understand? So that's the meaning of the approach temperature. So the minimum temperature difference between the hot sink and the cold sink, you understand? So that's the meaning of the temperature approach. So then you calculate the carbon fee if you want it to calculate the cost that is related with the carbon tax for the emission that the process will generate, you understand, as a result of the utilities, you understand, that you are using, or the process generally, if it is emitting carbon, CO2, carbon emission. Then you define the scope, that is the area that you want to analyze, because the model is okay, let me just define it first. because the model is defined to be, I'm much concerned about the train, so I duplicated most of the heat exchanging, the process that is related with the heat exchange or the heat exchange energy unit of block in this flow sheet that I call heat exchanger network train. You understand? Then we have the furnace that is supposed to be inside the column inside the heat exchanger network train. So these are all the furnace. This is the atmospheric furnace, and I have the vacuum furnace over here. And for the cooler, I make sure that it is inside the heat exchanger train. So this is the process. Because the process cannot be changed, that is, the product temperature cannot be changed. I must get the product temperature from the specification. I must get the crude inlet temperature, that is, it must be the furnace temperature that is coming out, must be, you understand. Then I must get the temperature of the temperature of the each of the pump around return must be constant, you understand. So all those will not be changing, but the heat exchanger network can be rearranged in order to make sure that there is less utility used in the network. You understand? That's the purpose of this work. And that's why I define it to be just the train. So you can see each of the cooler and the heat exchange, each of the cooler and the heater that we have in the flow sheet that I defined. They are all here, and the utilities that is corresponding utilities for each of the cooler and heater. To define the utilities, you have the utility 1, 2, 3. That's what the utility that I've defined over here, and you can define it here and use for each of the block. We have the first one is fired heater. It's fired heater utility. We have the water utility for the condensers, and the air utility, air fin cooler, for the coolers. You can say much about the definition of each utility. We have the energy price, it's just the default value, and the carbon tracking. Then for the water, there is no carbon tracking or sort, it's just the energy price. So to calculate the cost of the utility with respect to the flow of the utility. Then okay, go back. Okay, so after you are done with that, the next thing is to analyze the theoretical amount of heat that can be exchanged and the current setback that you're having. So it will take some time. Okay, it is done. So we have the total utility that is calculated for the heat exchanger train. This is the total addition of the heating and the cooling utility and the carbon emission that we are getting. You can see the flow rate of carbon, and we can see the associated costs of each of the utilities. We have the actual, target, available, and percent of the actual that we can save from the theoretical calculation of the heat exchanger network. It's going to do pinch analysis on the calculation. You understand? It's going to do pinch analysis on the calculation to calculate the theoretical amount of heat that can be exchanged between the hot and the cold streams in the heat exchanger network, and calculate the minimum amount of heating duty and the cooling duty that we need. You understand? So then you have the heating utilities here and the cost. You can see the cost is very, very low. I think if you go to more details on the utility, you understand why. Because the cost of water is very high compared to cost of air. So it's trying to make sure that it's suggesting I should use air. You understand? Because the cost of air is very small. So it's trying to increase the amount of air that is required. But it's not advisable to use air because the flow rate is very, very high, and there will be technical problem on that Then we have the hot utility, which is the fire heater, and you can see the cost of it. And this is the amount that can be saved for the water 100%, you understand, and the minimum temperature driving force for each of the utilities. Then we have the carbon emission. You don't have carbon emission for water and air. We only have for fire heater as a result of burning natural gas, you understand. Then we have the heat exchangers that we have in the flow sheet. You can see all the heat exchangers over here. So this is the heat exchanger that we have in the flow sheet. So, and the heater and the coolers, it tells us the inlet temperature and outlet temperature and the amount of heat that can still be recovered from the heat exchanger. You understand? This is the duty that we are currently recovering from the heat exchanger. Then we have the cold stream and the hot stream. So then there is one capability for this energy analyzer. It can calculate scenarios of heat exchangers design, reconnection, like suggest modification of the heat exchanger network to optimize the heat integration in the process, or add heat exchanger or add heat exchanger or relocate heat exchanger from one point to another. You understand? So I can tell you the default numbers of heat exchanger that I wish to add if it is available, or relocate amount of heat exchanger I want to relocate if it's available. You understand? So, and then I'm going to do the analysis, the test here, if it can see results for in a way to reduce the energy saving to to increase the process to be very close to the theoretical limits. So it's going to search for a solution. Okay, it is done. So for the modified heat exchanger, there is no solution that is found to increase the heat integration in the process. For the adding a new heat exchanger, it found 3 solutions, and the relocate it found 2 solutions. So for the solution 1 for adding heat exchanger, we have adding heat exchanger to the upstream to heat exchanger 37 and furnace. For example, check from the flow sheets, it's suggesting I should add 1 heat exchanger to the upstream of this heat exchanger 37 for the upstream. For example, the upstream of heat exchanger 37. So I should put a heat exchanger there. So this is the upstream for the heat exchanger 27, stream 60, which is coming at temperature of 367 Celsius. Then for the 31, then the downstream will be the cold side of the heat exchanger is going to be for the upstream of the furnace, which is our crude stream. This is the furnace. So this is the crude stream. So if we can increase the temperature of this crude stream, the duplicate is just to duplicate the stream. You understand? Because this is the main stream that is going to the column. This is the duplicate of the furnace in the heat exchanger train. So so I'm going to increase the temperature of this to higher temperature. So I should put it as the cold stream for another heat exchanger. So that's what this is suggesting. So what you should consider in all this is the extra capital cost. If it is minimal compared to others, then you can see this will increase the capital cost of the solution. Engineering is just about balance and making sacrifice, compromising. You understand? You can't get the right thing, but you should know what to sacrifice for others. You understand? You want to increase the efficiency, the integration. The process of burning a lot of fuel is not an efficient way. You understand? So, but you can just incur extra capital cost for the new heat exchanger to design. For, you understand, for the retrofit design. Then for this, the capital cost is very high, and even the energy saving is not as high as this. You can see this is having high energy saving. This is not even having any energy saving, and the capital cost is also very low. You understand? So that's why I'm going to try this. Then we have this to C792. It's also very high. The energy saving is also very high, but the capital cost is very very, very low, because the heat exchanger area is going to be higher than the new heat exchanger that you just or you buy. You understand? If you are just relocating this is going to increase the heat exchanger area for the one that we have. You understand? So, and you can see details about this by just clicking on this. It's going to take us to the energy analyzer and analysis environment. So you see the existing area of each of the heat exchanger and the one that you want to relocate. You can see this is the old area that you have. Then when you add this, it's going to increase the to new area. You understand? So, but if you are just if you are going to scenario of adding heat exchanger, you can see for the heat exchanger, it's just like what we have seen before. It's telling us that this is the new heating utility that we are going to be using, and this is the new cooling utility. So this is the percentage reduction, but the target is the theoretical limits. You can see this is the target. So we are trying to get to the targets. So then for the heat exchanger that you are adding is just 816.5, and the extra capital cost is this. So you can see the total cost of the process here, and these are just the other variable that is important: the temperature approach of the hot side and the cold side, and the load and the log mean temperature difference for the heat exchanger network. Then you can switch between each scenario for the heat exchanger to add and see the difference in order to make the right decision. So, and that's one thing. In order to see more details, because I'm going to try to do this suggestion, the first suggestion, that is adding this heat exchanger at 39 heat exchanger, option of heat exchanger 39 and furnace. I'm going to do that. So to see more details about the temperature specification for the heat exchanger, not just temperature approach, you have to go to detail. It's going to take us to Aspen Energy Analyzer, which is another software for doing energy analysis, heat exchanger design and analysis. So, and from the software, it's going to open this case in the Aspen Energy Analyzer. So I'm going to do that now. So it takes some time. So for the Aspen Energy Analyzer, we have just like typical the grid diagram for the heat exchanger network. You can see the splitting and how the heat exchanger, this represents the heat exchanger network, and you can see the heat exchangers here. So I'm going to be saying for this scenario, this is the third scenario for the relocation of the heat exchanger. So I'm going to go to the one for the first one that we have for the adding heat exchanger, which is this scenario over here. So we are going to have the calculation of the energy analysis here. So you can see the new area, then the payback here is 0.5404. Then the worksheet is here. For each of the stream, you have the utility, the inlet temperature of the utility, code 20 is going out at 25 for the cooling water. For the air, it's coming at 30. No, this is okay. Okay, it's coming at 30 and going back at 5. Then we have the water 20-25. Then we have the hot inlet and outlet temperature. Then for the heat exchangers too, we have all these the heat exchanger design. So then so I'm going to print a report on this for the worksheets, not just everything, just print the report on this scenario for the worksheet, so I can duplicate the heat exchanger over here. So okay, let me just create a new one here. 1111. So it will print the report. So okay, this is the report over here. Okay, so this is the worksheet. So I'll be using this. So I'm going to duplicate all this specification for the temperature in the heat exchanger design. So I don't really need this anymore. So go back to the simulation environment. So I want to duplicate this to increase the current simulation case hot and code utilities and get this reduction in the process by following the suggestion of this. So you go to the simulation environment. So I'm going to go back to the flow sheets. So in the flow sheet, just unlock the flow sheet. Then the first thing is to add the heat exchanger first. Let me add the new heat exchanger, which is here is heat exchanger 100. So I'm going to add this at this upstream of this Maya stream, and for the cold stream, then the oil stream is going to be stream 60 to 62A. You understand? So I'm just going to create a new, going to the palette there to pick the heat exchanger network block. So you go to exchanger, then you go pick the exchanger here. So I'm going to just drop it here. I'm going to give it a new name. $40. Okay, so okay. Okay, so for this, I'm going to reconnect it to the common. And how to make this better, let me do something over here. This I'm going to do something over here. For this, I'm going to draw it over here. Okay, it's better here. Okay, it's better like this. So, and I'm going to draw this up so that it is reasonable. So the next thing is to add the outlet stream. So this connect back, and this connect here. So this is I'm going to give it a name in same common name so that I can easily distinguish between them. So this is 60B. Okay, so I think everything is set up. The next thing is just to specify the temperature. So I'm going to be specifying the hot temperature for this by following this this flow sheet. So it's 17. The hot temperature is coming out at 304.1. degrees Celsius. Then I'm going to, because the temperature profile will change for the temperature specification for all the exchanger will change. So I'm just going to cross check all the temperature profile of all the heat exchanger one after the other. So I'm just going to do it from here. So I'm going to check from here. So we have one after the other. So we have the heat exchanger 39, specifying the cold temperature or hot temperature, which one is suitable. You understand? So this one is 301 degrees Celsius, 39, exchanger 39. I think it's over here. Just do for it here. Okay, cold outlet temperature. Okay, it's very close, basically the same thing. Then you go to the next one, 9, heat exchanger 9, heat exchanger 9, exchanger 9, code outlet temperature. So this one you have to reduce it to 90. Then you go to this one, heat exchanger 21. That's how you are going to do for the rest. Heat exchanger 21. Okay, so I'm going to skip this now for the rest. Okay, so you might want to disable this. Okay, so and to prevent error, so the next thing after heat exchanger 21 is heat exchanger 11. Heat exchanger 11. So I'm going to do for heat exchanger 11. Okay. So you are going to do that till the end of the heat exchanger, which is this is, I think this is the end. This one is also having utility 1. This one is utility 2. So this is the end of the heat exchanger and process heat exchangers. So I'm going to do heat exchanger 13. Heat exchanger 13. So heat exchanger 13. So to the end of heat exchanger 13. So then once I'm done, I'm going to solve the simulation first. So this is before I go for the energy analyzer. Let's check if the simulation is going to solve. Okay, the simulation encountered error. Might be all this. So let's check. It's a cooler. So let's see what happened. Okay, this is the product temperature. So I think the process wants to make sure that the APC cooler APC3, it wants to make sure that the product reach the specified temperature. So don't have to disturb yourself. So maybe because the duty is very, very small for the utility, so it's not able to calculate the utility usage. I'm going to do something, maybe it's going to work, just to force it to 0. I'm going to try and specify it again, and I'm going to do this. Okay, try and force it to 0 instead of disturbing myself there. Okay, good. Let's see if it is going to work again using that as, because it's just some bugs. Supposed to take it at same temperature. It's still not working. Okay, let's leave it at 204. Leave it at 0. Then let's leave it like this then. Okay, let's leave it like this so that we can do our thing. So after you are done, the next thing is to analyze it again by clicking this. You can analyze it again by clicking this. Okay, after it is done, you can see the saving potential is now 2.25%. So we are closer to the theoretical limit. So this is the amount of energy that can still be saved, you understand? So so you can see from the train, if you check the train, that the outlet temperature of the crude is very high now compared to what we have before. So we have optimized it to 312. Let me check the restream results. So this is the cold stream, 312.3 degrees Celsius. So it will reduce the workload on the furnace, and you can see the target and actual, they are very close now to the carbon emission target and actual. You can see the cost too, they are very, very close. You can say 1.1 1.8, 1.83. Then the utilities, the carbon emission, and the heat exchangers, they are now working very fine. And you can save this in a report by generating reports on Excel for the heat exchanger network. Okay, so the report has been generated. So you have the total utility, cooling utility, and everything. So if you want to do any other calculation, you can do it. So you have the cost in dollars and everything for the summary of the heat exchanger network design and integration with Aspen Plus. So you can see just adjusting the configuration of the process using by adding a new heat exchanger has increased the heat integration in the process and the with little amount of capital costs. So and that takes us to the end of this video. I believe you are able to learn something about heat integration in Aspen Plus. So if you like this video and you gain something, you should comment, like, and share this video to your friends and colleagues so that they can also gain the knowledge too. And you can check on me. You understand, if you are working on the same project or something like this, you understand, or you need something, you need help or something on your project, I am available. So and you can get me on my contact on the video. So thank you for watching. I really appreciate it.